Good day. In this video, we will discuss the concept of power. If you notice, none of the equations we have discussed so far mention time, include time in none of them. So today we're going to define a quantity that includes time for the first time. I want to define power as, these three lines mean definition, we defined power as the change in energy over the change in time. So this basically is the time rate at which energy is transferred in on or out the system. This could also be work per unit of time, but if it's work, then this is force. It's the same as if I write force dot displacement, and notice that the force and the displacement together is the velocity. So these are a few ways in which you can define the power. In this case, this is the instantaneous power. If you want the instantaneous power, well, you do the derivative, okay? If not, well, is the average power. There you go. That's the definition. So if that's the case, then you can find how power, if we use this definition, this is the average power. Power is energy is power times time. So from now on, I'm going to be dealing with the average power, like so. Notice that the units for power will be the units of energy, which are joules per unit of time, which is second, and 1 joule per second. Well, that's 1 watt. In honor of James Watt, who refined the steam engine. The British unit for power is the HP, horsepower, and 1 horsepower, and that is equal to 746 watts. So if you ever buy a car that says this thing is 300 horsepower, well, you know it's just power, and then you can convert it to watts if need be. So let me tell you about another unit related to power. If you have a microwave at home, and then an oven, and then it's probably rated 1,000 watts, well, that's 1 kilowatt, right? And if you use this thing for 1 hour a month, let's say, which is not just 2 minutes every day for a month, times 30 days, well, there you go, 1 hour a month. Then you have spent 1 kilowatt times 1 hour, right? That's, if I want energy, I multiply power times time. So this will be my energy. The energy spent by the microwave was 1 kilowatt times 1 hour, which is 1 kilowatt hour. Yes, we could put this, let's do it. This is 1,000 watts or joules per second, and this is 3,600 seconds. So of course this gives you 3.6 times 10 to the 6 joule. So it's about 4 million joules or 1 kilowatt hour. And the thing is, Hydro-Quebec charges you on average 8 cents every kilowatt hour. 8 cents per kilowatt hour. That's the rate. Of course, if you consume more in the winter or during peak hours, it's going to change. But let's say 8 cents per kilowatt hour. Oh, every hour of this microwave is costing you 8 cents. Let's work on this example. We have an elevator that is going to move up at constant velocity. So the acceleration is 0. Right? The elevator, of course, goes up because there's a tension on the cable. There's people inside. My God. There's people inside, and it says that there is also friction. So there's going to be the weight, and there's also going to be friction going on. if we add all the forces in y, we know this must be equal to, it must be equal to 0 because there's no acceleration. So tension going up minus the weight minus the friction must be equal to 0. So the tension is the weight plus the friction. We know the mass, we know the friction, the combined mass will be 1600 kilograms of the elevator plus the 200 kilogram people. So first question is, how much power must the motor deliver to lift the elevator at constant speed of 3 meters per second? This is going to be power average. So we said it's change of energy with change in time, which is the work over time, or as I told you, is the force times the velocity. Well, this has to be a dot product because it comes from the dot product of the work. So the force, well, is the tension plus the friction dot the velocity, which is given by us. So the velocity, you see these two vectors are parallel, the tension vector and the velocity vectors are parallel. So that's going to be cosine of 0, so is 1. So all we have to do is multiply all the terms together. So the mass, combined mass, is 1800 kilograms. The friction is 4000. Oh, that I'm missing gravity here, sorry. Times 9.81 meters per square second plus the 4000 newtons of friction, and all of this times the velocity, which is 3 meters per second. I'm in kilogram meter second, so my power is going to be equal to 6.49 times 10 to the 4 watts. Now it's very hard, it's going to be very hard for you to get a motor that with this rating. So let's convert this. We're going to say that 746 watts is 1 horsepower, and this is going to give us roughly 87 horsepower. So that's a big motor. Now they tell us to do it again, but now the elevator, instead of going at constant velocity, is going to be accelerating, right? Accelerating at 1 meter per square second. So what's the new power? So let's do it here. What we're going to have is in the sum of forces now, tension minus the weight minus the friction is going to be ma, positive, because the acceleration goes up. So you see now the tension is different, is weight plus friction plus ma. So the power is going to be force dot velocity. So it's going to be the force is all that is the tension, the weight plus the friction plus ma times v. So the power now, well, I have to do all the numbers again. 1800 times 9.81 plus 4000 plus 1800 times 1, and all of this times 3. And now we get, no, excuse me, it's not 3, it's just v, because we don't have a constant velocity. I just erased this. So this is going to give us 2.34 times 10 to the 4 times v. So in this case, the power is still the instantaneous power, the average power is still a function of how fast you are going. Now, at the moment, when the velocity is 3, like here, eventually it's going to be 3. You start at 0, it's going to be 3, then the power will be 7 times 10 to the 4 watts, which is larger than this. And of course, because the new motor, which is more powerful than before, not only needs to keep accelerating the elevator. So there you go. That's a little example using the concept of power.